welcome to this problem walkthrough. Today, we'll be tackling problem number 1386, Cinema Seat Allocation. In this problem, we'll explore how to allocate seats efficiently in a cinema while ensuring group preferences are met. Let's dive in and break down the solution approaches step by step. Imagine a cinema with multiple rows of seats, each row having exactly 10 seats numbered from 1 to 10. The goal is to seat as many families of 4 as possible in the cinema while adhering to social distancing rules. To qualify, a family must occupy a block of 4 contiguous seats, like seats 2 through 5 or 6 through 9. These seats must not overlap with other families or be split apart. However, some seats in the cinema might already be reserved, meaning they are unavailable for use. You're provided with an array called reserved seats, where each entry specifies the row and seat number of a reserved seat. Using this information, your task is to calculate the maximum number of families that can be seated in the cinema without violating the rules. The rows in the cinema are numbered from 1 to n, and each seat within a row is numbered from 1 to 10. For the output, you need to return an integer representing the maximum number of families of 4 that can be seated while following the social distancing policies. Let's look at some examples to clarify how this works. In the first example, the cinema has 3 rows, and there are several reserved seats across these rows. For instance, row 1 has seats 2, 3, and 8 reserved, while row 2 has seat 6 reserved. Based on this input, the output is 4, meaning that 4 families can be seated in total while adhering to the rules. Now let's break down the reasoning behind the first example. In row 1, because seats 2, 3, and 8 are reserved, the only block of 4 contiguous seats available is 4, 5, 6, 7. In row 2, even though seat 6 is reserved, 2 valid blocks of seats remain, 2, 3, 4, 5, and 8, 9, 10. Row 3 has seats 1 and 10 reserved, but there are still 2 valid blocks, 2, 3, 4, 5, and 6, 7, 8, 9. This gives us a total of 4 families across the 3 rows. In the second example, there are 2 rows, and the reserved seats include row 1 seat 8 and row 2 seat 6. Here, row 1 only has space for 1 family in block 2, 3, 4, 5, and row 2 only has space for 1 family in block 8, 9, 10, resulting in an output of 2 families. For the second example, as we saw, the reserved seats prevent more than 1 family from sitting in each row. In the third example, the scenario is even simpler. There are 4 rows, but no seats are reserved. Since there are no restrictions, each row can accommodate 2 families, 1 in the left block, 2, 3, 4, 5, and 1 in the right block, 6, 7, 8, 9. With 4 rows, this results in 8 families in total, as each row contributes exactly 2 families. This example highlights the ideal case where no seats are reserved, maximizing the number of families that can be seated. To summarize the seating rules, a family of 4 must occupy one of 3 possible seat blocks: the left block, 2, 3, 4, 5, the right block, 6, 7, 8, 9, or the middle block, 4, 5, 6, 7. Importantly, families cannot occupy seats that are partially reserved or split across these blocks. Rows with no reserved seats can fit exactly 2 families, but rows with reserved seats need to be carefully checked to determine which blocks, if any, are still available. Finally, because the input size can go up to 10,000 reserved seats, your solution needs to be efficient and handle these constraints effectively. By following these rules and constraints, you can calculate the maximum number of families that can be seated in the cinema. To solve the cinema seat allocation problem, we considered a few different approaches. The most straightforward method is the brute force approach. Here, we simulate the seating for all rows and seats. Each row is represented as an array of size 10, where reserved seats are marked as occupied based on the input. Then, we evaluate all possible 4 seat groups, such as seats 2 to 5, 4 to 7, and 6 to 9, checking that they don't overlap with any reserved seats. For every valid group, we keep a count and then sum these across all rows. While this method is easy to implement and debug, it has significant downsides. The operations required grow quickly with the number of rows and reserved seats, making it inefficient for large inputs. Specifically, the combination of rows and seat checks can lead to a time complexity of n squared in the worst case, which is not scalable for high input sizes. To address this, we explored more efficient solutions, like bit masking and greedy strategies. The optimized approach using bit masking streamlines the process by focusing only on the critical seat groups, 2 to 5, 4 to 7, and 6 to 9. Instead of simulating all seats, we use a 10-bit binary representation for each row, where a 1 indicates a reserved seat and a 0 means it's free. For example, if seats 2, 4, and 7 are reserved, the bit mask would be 010, 100, 0100. Using this representation, we perform constant time checks to determine if a specific group of seats is available. First, we check if the group, 2 to 5, is completely free, then 6 to 9, and finally, if necessary, 4 to 7. This significantly reduces redundant operations, as the checks are performed using simple bitwise operations. The result is an O(n) time complexity overall, since each row is processed independently in constant time. While bit masking is efficient, it does require a slightly more complex implementation. Alternatively, we also considered a greedy approach that uses a dictionary to store reserved seats for each row. Here, the algorithm only evaluates reserved seat numbers for each row and checks the 3 possible groups. This method avoids simulating all 10 seats, making it simpler than bit masking, with a space complexity of O(r), where R is the number of rows with reserved seats, and a time complexity of O(n). However, it is still slightly slower than bit masking due to the added overhead of set operations. After evaluating these approaches, we chose the optimized bit masking strategy as the best solution. This decision was based on key observations about the problem. First, each row operates independently, so we can process rows one by one without worrying about interactions. Second, only 3 specific seat groups, 2 to 5, 4 to 7, and 6 to 9, are relevant for accommodating families while maintaining social distancing. Finally, the reserved seats can be represented compactly using bit masks, which reduce redundant checks and enable constant time operations for each row. Compared to the other methods, bit masking achieves the best balance between speed and complexity. While the brute force method is simple, it becomes inefficient for larger inputs due to its O(n)² time complexity. The greedy approach with set representation improves upon this by reducing space usage and time complexity to O(n), but it is still slower than bit masking. In contrast, bit masking achieves O(n) time complexity with O(1) space per row, making it the fastest and most efficient choice overall. Although the implementation is slightly more involved, the performance benefits far outweigh this minor drawback. For scenarios where simplicity is more critical than speed, the greedy approach remains a viable alternative, but for optimal performance, bit masking is the clear winner. In this problem, we are tasked with determining the maximum number of families that can sit together in a cinema, given certain reserved seating constraints. Each row in the cinema consists of 10 seats, and families of 4 can sit together if their seats are consecutive within predefined groups, 2, 3, 4, 5, 4, 5, 6, 7, or 6, 7, 8, 9. However, some seats in the cinema are reserved, which makes it impossible to use those seats. To solve this, the first step involves parsing the input to identify which seats are reserved. Each reserved seat is represented as a tuple of its row and seat number. We then organize these reserved seats row by row using a dictionary. In this dictionary, the keys represent the row numbers, and the values are sets of reserved seat numbers. This setup allows for efficient O(1) lookup when verifying if a seat is reserved. Once the reserved seats are grouped row by row, the next step is to process each row individually. For rows with no reserved seats, we can directly allocate the maximum of 2 families, one group in 2 to 5 and another in 6 to 9. For rows with reserved seats, we perform specific checks to determine which groups are still available. This includes verifying the availability of the groups 2, 3, 4, 5, 6, 7, 8, 9, and 4, 5, 6, 7, ensuring that no reserved seats are present in these ranges and avoiding overlap between groups whenever possible. After processing each row, the total number of families that can be seated is calculated by summing up the family counts for all rows. We also need to account for edge cases. For instance, if no reserved seats or rows are provided in the input, we can directly return 2*n, as every row can accommodate 2 families. On the other hand, if all seats in a row are reserved, no families can be seated in that row, resulting in a count of 0 for that row. When dealing with rows that have only a few reserved seats, it's important to ensure that we handle them efficiently, avoiding unnecessary checks. A few key insights are crucial for solving this problem effectively. First, the groups 2 to 5, 4 to 7, and 6 to 9 overlap partially, so it's important to check them carefully to avoid double counting. Second, by using a dictionary to store only the rows with reserved seats, we reduce the problem size significantly. Instead of processing all n rows, we only process rows with reservations, leading to an optimized approach. Finally, the use of predefined groups for seating checks simplifies the logic and reduces the overall complexity. Using data structures like dictionaries to map reserved seats and counters to track family counts ensures both efficiency and clarity in the implementation. Now, let's analyze the complexity of this approach. The time complexity is O, R, where R is the number of rows with reserved seats. This is because for each row, we perform constant time checks for the three predefined groups. The space complexity is also O, R, as we only store the reserved seat data for rows with reservations in the dictionary. This ensures that we only use memory for the rows we need to process. The pseudocode for the algorithm is straightforward. First, we parse the reserved seats into a dictionary where each row key maps to a set of reserved seats. Then, we initialize a counter for the maximum number of families. For every row from 1 to n, we check if it has reserved seats. If not, we add 2 families to the count, one for each of the 2 non-overlapping groups. For rows with reserved seats, we check each of the 3 groups 2, 3, 4, 5, 6, 7, 8, 9, and 4, 5, 6, 7 to determine availability. If a group has no reserved seats, we mark it as available and increment the count. This ensures that we efficiently determine the maximum number of families for each row, while accounting for reserved seats. Finally, if none of the outer groups, 2, 3, 4, 5, or 6, 7, 8, 9, are available, we check the middle group, 4, 5, 6, 7. If this group is free, we add 1 to the count for the row. After processing all groups for a row, we update the total number of families with the count for that row. Once all rows have been processed, we return the total maximum number of families that can be seated. This approach ensures that we handle all rows efficiently, account for reserved seats accurately, and avoid double counting overlapping groups. By combining careful group checks with efficient data structures, this algorithm achieves the desired results while remaining optimized for both time and space. Here, we start by defining the solution class and implementing the function maxNumberOfFamilies. This function takes 2 parameters, n, which represents the total number of rows in the cinema, and reserved seats, which is a list of reserved seat positions. To handle the reserved seats efficiently, we use a defaultIct from the collections module, mapping each row to a set of reserved seats. This helps us quickly check which seats in a row are unavailable. Next, we define 3 potential seat blocks that can accommodate a family of 4, the left block, spanning seats 2 through 5, the middle block, spanning seats 4 through 7, and the right block, spanning seats 6 through 9. We then initialize max_families to 2*n, assuming every row can initially accommodate 2 families. Now, for each row that has reserved seats, we check whether any of the seat blocks overlap with the reserved seats in that row. If both the left and right blocks can fit, we retain the assumption of 2 families for that row. However, if only one block fits, we reduce the total count of families by 1. If none of the blocks, left, middle, or right, can fit a family due to overlapping with reserved seats, we reduce the count of max_families by 2, as no families can be seated in that row. Finally, after iterating through all rows with reserved seats, the function returns the total max_families, which represents the maximum number of families that can be seated in the cinema. This approach ensures we handle edge cases effectively, such as rows with no reserved seats or rows with reserved seats that block multiple configurations. By leveraging the defaultIct and the concept of disjoint sets, this solution remains efficient and easy to understand, even for larger inputs. Here, we start with the Java implementation of the problem by importing the necessary packages and defining the solution class. The main method, maxNumberOfFamilies, takes 2 inputs, the number of rows in the cinema, n, and a 2D array of reserved seats, where each entry represents a specific seat that is already occupied. To manage the reserved seats, we use a hash map called reservedMap, where the key is the row number, and the value is a set of reserved seat numbers in that row. For each seat in the reserved seats array, we add its seat number to the corresponding row in the map, ensuring that we have a complete record of all reserved seats for each row. Next, we define 3 blocks that represent possible seatings for a family of 4, the left block, middle block, and right block. These blocks correspond to specific seat ranges within a row. Initially, we assume that each row can accommodate 2 families, setting max families to 2 times n. We then iterate through the rows in the reserve map, checking which blocks are available for seating. To determine this, we use the collections.disjoint method to check whether there is no overlap between the reserved seats and the seats in each block, starting with the left block. If both the left and right blocks are available in a row, we simply continue since we retain the assumption that 2 families can be seated. However, if only one block, either the left, middle, or right, is available, we reduce the max families count by 1, as only one family can fit in that row. If no blocks are available, meaning none of the left, middle, or right configurations can accommodate a family, we reduce the count by 2. This logic ensures we correctly account for rows where fewer families can be seated due to reserved seats. Finally, after processing all rows in the reserve map, we return the max families value, which represents the maximum number of families of 4 that can be seated in the cinema under the given constraints. To solve the problem, we start by considering the simplest case where there are no reserved seats in the cinema. Here, the input specifies 3 rows and an empty list of reserved seats. First, we initialize our reserved underscore map as an empty dictionary using defaultdict set. Since there are no reserved seats, the reserved underscore map remains empty throughout. Next, we assume that each row can accommodate 2 families, as there are no restrictions. Multiplying the number of rows, 3, by 2 gives us an initial maximum of 6 families. Since there are no reserved seats to process, we directly return the calculated value, which is 6. This result makes sense because all rows are fully available, allowing 2 families per row without any issues. Now we consider a case where reserved seats are present in the cinema. Here, there are 2 rows, and the reserved seats are in specific positions, seats 4 and 5 in row 1, and seat 8 in row 2. First, we initialize reserved underscore map and populate it based on the input, resulting in row 1 having reserved seats 4, 5, and row 2 having 8. Initially, we assume each row can fit 2 families, giving us a total of 4 families. Starting with row 1, we check the 3 possible blocks of seats: the left block, 2, 3, 4, 5, the middle block, 4, 5, 6, 7, and the right block, 6, 7, 8, 9. The left block overlaps with the reserved seats, making it unusable. Similarly, the middle block also overlaps. However, the right block is unaffected, meaning only one family can fit in row 1. Therefore, we reduce the total capacity by 1, leaving us with 3 families. Next, for row 2, the reserved seat is 8, and we evaluate the same 3 blocks. The left block, 2, 3, 4, 5, and the middle block, 4, 5, 6, 7, remain completely usable as they do not overlap with the reserved seat. The right block, however, is affected by the reserved seat. This allows 2 families to fit in row 2, so we retain the current count of 3 families. For row 2, we see that the right block, 6, 7, 8, 9, overlaps with the reserved seat, 8, making it unusable. However, since the left and middle blocks remain free, 2 families can still be accommodated in this row. Thus, the total number of families remains 3. Returning this value, the result is 3 because row 1 fits 1 family, and row 2 fits 2 families. Moving to the next example, we have a scenario where every row is heavily restricted by reserved seats. In this case, there are 2 rows, with row 1 having reserved seats 2, 3, 4, 5, and row 2 having 6, 7, 8, 9. This setup significantly limits the seating options, as each row has entire blocks of seats blocked by reservations. We begin by initializing reserved underscore map and populating it with the reserved seats from the input. Row 1 has reserved seats 2, 3, 4, 5, and row 2 has 6, 7, 8, 9. Initially, we assume each row can fit 2 families, giving a total of 4 families. Starting with row 1, we evaluate the 3 blocks of seats. The left block, 2, 3, 4, 5, overlaps entirely with the reserved seats, making it unusable. The middle block, 4, 5, 6, 7, also overlaps, and the right block, 6, 7, 8, 9, does not fit either. Since no blocks are available, no families can fit in row 1, and we reduce the total capacity by 2, leaving 2 families. For row 2, we repeat the process. The left block, 2, 3, 4, 5, does not overlap, but it is too far from the reserved seats to accommodate a family. The middle block, 4, 5, 6, 7, and the right block, 6, 7, 8, 9, both overlap with reserved seats, making them unusable. Consequently, no families can fit in row 2 either, reducing the total capacity by another 2 families. This leaves a final result of 0, as neither row can accommodate any families. The result for this example is 0 because both rows are fully reserved, leaving no space for families. To summarize the key insights, rows with no reserved seats can always fit 2 families. If reserved seats overlap only one of the 3 blocks, the row's capacity is reduced by 1 family. However, if reserved seats overlap all 3 blocks, the row's capacity is reduced by 2 families, effectively leaving it unusable. This approach processes rows independently, ensuring that the total number of families is maximized while efficiently handling the constraints imposed by reserved seats. To analyze the time complexity of the solution, we can break it down into a series of steps. First, we build the reserved underscore map, which maps each row with reserved seats. This involves iterating through the reserved seats list, which has a length of m. For each reserved seat, we add it to the appropriate set in the map. Since adding to a set is an O(1) operation, the total time for this step is O(m). Next, we iterate over the keys in the reserved underscore map, which correspond to the rows with reserved seats. Let's call the number of these rows k. For each row, we check the 3 possible blocks, left, middle, and right, to see if families can be placed. These checks are efficient because the blocks are constants in size, containing only 4 seats each. Determining if a block is disjoint with the reserved seats takes O(1) time per block, so the total time for this iteration is OK. The final step involves calculating how many families can fit in rows that are not in the reserved underscore map. Since these rows have no reserved seats, we can assume 2 families can fit in each row. This calculation is a constant time operation, requiring O(1) time. Combining all the steps, we have O(m) for building the map, OK for iterating through the reserved rows, and O(1) for the final calculation. Thus, the total time complexity is O(m) plus k. Since the number of unique rows with reserved seats, k, is always less than or equal to the total number of reserved seats, m, the time complexity simplifies further to O(m). This means the solution runs efficiently, scaling linearly with the number of reserved seats. Now, let's consider the space complexity. The primary contributor to space usage is the reserved underscore map, which stores reserved seats for each row. This map will have at most k entries, where k is the number of rows with reserved seats. Each entry is a set that holds up to 10 reserved seat numbers, as there are only 10 seats in a row. In the worst case, all reserved seats are unique, and the space needed for the reserved underscore map is proportional to the total number of reserved seats, or O(m). Additionally, the predefined seat blocks left underscore block, middle underscore block, and right underscore block are constant in size, each containing 4 elements. These require only O(1) space. Finally, the solution uses a few auxiliary variables like max underscore families, which also take constant space. Therefore, the total space complexity is O(m), driven by the storage requirements of the reserved underscore map. When comparing the optimized solution to a brute force approach, the differences in efficiency become clear. A brute force method would iterate over all n rows and check every possible seat combination for each row. While checking the left, middle, and right blocks for a row is O(1), iterating through all rows would take O(n). Additionally, for each row, the brute force approach would need to iterate over the reserved seats list, which takes O(m) time. This results in a total time complexity of O(n*m), which is highly inefficient for larger inputs. In contrast, the optimized solution focuses only on rows with reserved seats, reducing the rows to process from n to k. By leveraging the reserved underscore map, it achieves a time complexity of O(m). The space complexity remains O(m) in both cases, but the optimized solution drastically improves the runtime, making it far more suitable for large-scale problems. To understand the solution's performance better, we can evaluate it in different scenarios. In the best case, where no rows have reserved seats, the algorithm quickly calculates the maximum number of families that can fit, requiring only O(1) time for initialization. In the average case, reserved seats are scattered across a few rows, so the time complexity is O(m), as we still need to process all the reserved seats. In the worst case, every reserved seat belongs to a unique row, meaning k equals m. Even in this scenario, the time complexity remains O, m, as the algorithm processes each reserved seat efficiently without unnecessary computations. Overall, the solution is robust, maintaining an O, m, time complexity and O, m, space complexity across all cases, ensuring consistent performance even under varying input conditions. Let's discuss some common mistakes that candidates face when solving the cinema seat allocation problem. First, a frequent issue is misinterpreting the problem statement. For instance, some might assume that groups of 4 people can overlap in their seating arrangements, even though the constraints clearly prohibit this. It's essential to carefully read and clarify the rules as well as any edge cases before starting your implementation. Another common mistake is using inefficient methods to check seats. Beginners often iterate over all seats in a row, which can become computationally expensive, especially when reserved seats are sparse. A better alternative is to leverage data structures like sets or hash maps. Additionally, overlooking edge cases, such as rows without any reserved seats or rows that are fully reserved, can lead to incorrect outputs. Always ensure your solution explicitly accounts for these scenarios. Lastly, overcomplicating the solution is another trap. Some candidates use advanced data structures or algorithms when a simpler greedy or pattern-based approach would suffice. Overcomplication can increase the potential for bugs and unnecessary runtime overhead. Now, building on these points, another mistake is failing to optimize for sparse inputs. When reserved seats are sparse, iterating through rows without reservations leads to wasted computations. By analyzing the structure of the input, you can avoid unnecessary processing and improve efficiency. Moving on to interview insights, many seating problems rely on recognizing patterns. For instance, identifying groups of 4 or specific seating configurations can simplify the problem into manageable subproblems. Greedy strategies are also helpful here, as they prioritize placing groups in the most constrained sections first, ensuring the rest of the space is used efficiently. In interviews, be proactive about discussing edge cases. Scenarios like rows that are fully reserved, rows with no reservations, or cases with multiple valid solutions can often be a focus of interviewer questions. Finally, optimization is key. Even if you begin with a brute force approach, discussing how to refine it shows your ability to think critically and improve performance. Let's explore some related problems that share similar concepts or strategies. First, LeetCode 1221, split a string in balanced strings, involves partitioning a sequence based on constraints, which is similar to dividing seating arrangements. LeetCode 763, partition labels, also focuses on dividing sequences, but here the goal is to group elements with specific properties. Then there's LeetCode 1029, two-city scheduling, which is another optimization problem. It requires minimizing costs while adhering to given constraints, a concept that parallels the cinema seating problem. Lastly, LeetCode 1094, carpooling, deals with managing group constraints and capacity limits, again reflecting the need to balance restrictions while finding an efficient solution. Familiarity with these problems can help you identify patterns and approaches that carry over to seating allocation tasks. Finally, let's examine alternative approaches and their trade-offs. The brute force method involves simulating all possible seating arrangements for each row. While straightforward, this approach is inefficient for large inputs, with a time complexity of O, n*m, where n is the number of rows and m is the number of seats per row. A more efficient option is the greedy approach, which focuses on placing groups in the most constrained sections first. This method improves runtime but requires careful handling of edge cases. Using a hash map or set to track reserved seats is another optimization. This reduces unnecessary iterations, especially when inputs are sparse, achieving a runtime of O, k, where k is the number of reserved seats. For certain variations, you might also consider the sliding window technique. This method efficiently checks for valid group placements and balances simplicity with performance, though it's not always suitable for every version of the problem. Each of these methods has its strengths and weaknesses, so it's important to choose the one that best fits the input size and constraints. Great job! We covered the key insights and solution strategies for problem number 1386, cinema seat allocation. Remember, efficient seating allocation mirrors real-world optimization challenges, so understanding constraints and designing scalable algorithms is essential. Thank you for watching, and I'll see you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!